It should be growing at a rate of 6.82. That's probably also too much. So in that sense, Pepsi is also expensive. In fact, if you kind of make a comparison, Pepsi is more expensive than Coke because Pepsi requires a long-term growth rate of 6.8%. Coke requires about 6.4, I think. That zero point 0.4 is a big number. I mean, at 6.82, you get 175.91, 154.46. Let's look at the difference. It's a 14% extra valuation, 6.82 versus 6.4. So that means, again, taking this analysis seriously, which you should never do. These types of analyses, even for established firms, should only give you possible trading ideas. Once you realize, okay, there could be something to the argument that Pepsi is more expensive than Coke, then I could think I should buy Coke and short Pepsi. Since they're pretty much in the same industry, you have no overall market risk as long as you believe your belief that Pepsi is too expensive is satisfied, you're gonna make money over the long term. Fine, but that 14% is pretty good. Again, you should never take these types of analysis seriously. Even when you do, that required rate should be a really firm rate. And we're going to talk about how to approach that in chapter 11 and 12 pretty much. But right now we take it as gospel or Quran or whatever you think is holy to you. Something God said, or as I call the divine programmer. I truly believe, not believe, but I suspect that we live in an AI world. And I'm going to believe that even more when we could create an AI, uh, you know, that could actually learn about the system that created it. That's what physics is all about, quantum physics and astrophysics. We are able to learn essentially God's design, at least approximate it, let me put it that way. But when an AI is able to learn the rules of the program that created it, then I'm going to believe that theory. Again, it's a theory. I'm sorry, it's not a theory, it's a conjecture. What's the difference between a conjecture and a theory? Conjecture is something that you suspect that is true. A theory is a set of conjectures for which there is a lot of scientific evidence. It makes predictions, and those predictions come true. Some people say, oh, theory of relativity is just a theory. It is not just a theory, okay? That's why they don't want to believe it. It is not a theory. It made predictions that was otherwise not known. It predicted that there will be things that are called black holes. In 1916, oddly, there's a German guy named Schwarzschild, which literally means black child, uh, solved Einstein's equations and predicted that there must be black holes. But there's so much gravity, even the light cannot escape. It's about the curvature of the space-time. It's so steep, for the light to escape, it should be a little bit flatter than that. It can't. It just hits the curvature and goes back. It's that simple. And we now know that there are things called black holes. Einstein in 1915 predicted that when two really massive things collided, like two black holes or two neutron stars, that will create gravitational waves in space-time, and that's going to travel at the speed of light. That was one of the solutions of Einstein's equations. About 5 years ago, we actually observed gravitational waves at the very time we observed the flash of the uh, merger of two neutron stars. So now we know by experiment uh, gravity travels at the speed of light. It's not instantaneous, as Newton assumed. Actually, Newton simply assumed that there is something called gravity. He didn't make an argument about why it's there. Einstein made an argument that it was there because of the curvature. I mean, the man became, why he became famous? According to theory of general relativity, when there's a massive source of gravity, light that comes behind that should curve around that. Okay. And people said, there's no such thing. Light is going to travel straight up. What they didn't realize is light travels straight up in that geometry. This is a geometry. It's not Euclidean. It's curved geometry. Here's a straight line is actually a circle. Okay. On this portion, a straight line is a straight line, but on this portion, it's not. So in curved space-time, a straight line is actually curved. In 1919, there was a simple way to test this. There are certain stars during winter times. They are behind the sun, so we can't see them during daytime. Okay. At nighttime, on the other part of the season, we can see them because sun is on the other hand. So we know where they seem to be when sun is not in front of it. But during a solar eclipse, sun cannot hide their light. So if they're slightly behind the sun, according to general relativity, we should see them. We should see those stars at a slight distance to where they should be. And it came out that I think it was accurate up to 4 digits. This is using computational technology of 1919. Then Einstein became the guy who bent the light. No, he didn't bend the light. The light simply travels, a straight line, but the space is curved. That's the problem. Now, that's the theory. It makes predictions, and those predictions, by and large, are verified by experimental stuff. Quantum theory has a lot of predictions, and a lot of them come to be true. For example, you send single light photons through 2 little holes. If the light flows as a particle, you should have basically 2 little circles of dots on a photographic plate. If it travels as a wave, you should see certain interference. But if it's a quantum wave, it's a completely different pattern. How do you know? You get that completely different pattern, and your concept of reality is completely collapsed. But it's still just a theory, right? Accurate up to 15 digits, by the way. And that's pretty much the end of the efficiency of our computers as far as precision. Double precision real numbers, they're precise up to 15, 16 digits. That's it. So just because something is a theory doesn't mean that it's not real. Oh, they say, oh, I don't believe that theory. Theories are not for you to believe. And you can criticize them. You can say they can't handle these, they can't handle that. But theory is science. Your belief is not required. Just like here, you have models to the extent that they do a good job predicting the value of a stock. That model is effectively science. But not all scientific models are useful everywhere. I mean, a lot of sailors are still using the old Colombian star charts for navigation. Why? It works for them. You know, they don't have to go to Mercury. If you're going to send a rocket to Mercury, you need different charts. But if you're going to navigate from, Portugal to Newfoundland, the old charts is just good enough. You just need to know where north is and how much you traveled. That's it, done. All right. Let's stop here. Next week, we're going to do more problems with these and talk about other features of stocks. And I'll do chapter 7 homework and quiz after you guys come back from spring break. I don't want to send you guys such a break with an assignment.